this will be then our intro to columns. Wood columns. This image on the screen is the Zollomar in Bad Dürrheim, which was a project that Klaus Linkwitz did, and entirely out of wood. In fact, I was privileged to tour it with Klaus Linkwitz. He took us down there, and because I was at the university in Stuttgart, and Linkwitz taught there, and took a group of, I was a doctoral student at that time, of us down there to look at it. Beautiful structure, entirely out of wood. In fact, even the fasteners were pegs, and the reason was it's a salt bath, like we have in, don't we have in Arkansas or someplace salt springs, or hot springs, Arkansas, what is that called? Anyway, I've never been there, but I've been to the Zollomar, and it is a natural saltwater spring. So people love to go there, particularly in winter, and bathe in this hot water natural salt spring. Well, of course, that pool there on the inside does have a bit of mist coming off of it, and it's a salty mist. So they definitely didn't want a steel structure, and they then developed this completely wood. It's a kind of a grid shell, but a grid shell built out of laminated timber, not your typical, not like Fry Auto's ones that were lifted in place. This one, each of those beams is a prefabricated glulam piece that was set in place, and then the other pieces around it. And the columns there were these beautiful tree structures, branching glue laminated columns that then held that kind of oculus, so all naturally lit inside. And you'd swim. The fun part was you swim over to the edge of this. You can't quite see it here, but you'd swim over this way, and you'd come to the edge of the building, and you could swim under the edge of the building and come outside in this further pool of, they had a spring water outside, so that, you could swim out there, jump out, make a angel in the snow, and then jump back in the hot water and swim inside. So this is a pretty popular resort, but a beautiful structure that Linkwitz did all the engineering, and I think I have a whole separate lecture on that, the erection of it and whatnot, but worth the image, I guess. Okay, so in terms of designing, or in terms of any structure, we look at three different things, right? Strength, stability, and serviceability. And in terms of strength, when we were looking at the oh, hey, I could get my little, should I use a pen or a laser pointer? Oh, I see. Then I can't write on it though. Okay. In terms of flexure that we looked at earlier, we're talking about MC over I, VQ over IB. Those are the simple strength calculations. Stability was handled by stability factor, right? CL. And that had to do with lateral torsional buckling in flexure. So that's where all the stability is wrapped up. Serviceability with beams is mostly deflection. That's what we look at. I guess maybe bearing, although it has more to do with, no, not really, because well, only in terms of how much it deflects, I guess, has more to do with the crushing. So that would be more back up with strength. In axial members, the strength is simply P over A. If you're not considering the buckling aspect of it, then the only criteria is the crushing of the material in axial load. So that axial compression would just simply be P over A. Again, the stability is handled with this stability factor, or the buckling factor. For columns, it's CP, and you can see it's very similar to the buckling factor that was used with the beams. There's slight different. This element here, C, that comes in is for distinguishes between dimension lumber or blue laminated, or I think there's a third choice. There's different wood types. And otherwise, you do calculate the Euler buckling. This is the Euler buckling equation, and set it at a ratio of the other allowable stress values for compression, and then you calculate this CP. Right, and then in stability, in serviceability, yeah, I put down their bearing, but only in the extent that the column changes height, that the bearing crushes or something that would become a height issue, and then there are not too many serviceability issues I could think of with axial loads, actually. Okay, so the fellow who first did the calculations, and there's a famous story that he did it on the back of an envelope kind of thing, that there were some engineers that were trying to come up with a formula for predicting the buckling of a column, because up to that time they had always just tested them individual members until they buckled, and there were tables available for individual members, like, if you had a 2x4, but then you'd have to have a table for every different type of wood, and you'd have to have a table that included every different height, and you'd have to test all of these individually and put it, so they thought certainly there is an equation that would describe this phenomena without testing each one every time. So I think they were Dutch, and they sent a letter to Euler, who was at that time, I think, in Berlin, and he had been working on, he'd been studying elastic deformation, elastic curves, and that's why they wrote him, because that's what it is, an elastic buckling curve. And he did the derivation and the calculation, came up with the formula, and sent it back to him like a day later, literally, like written on the back of their letter. And the only thing he didn't exactly include was, I think, the K factor, and he mentioned it in his letter. He said, well, there's certainly a condition that's some factor that's dependent on the infixity or whatever, but you can figure that out from testing. So it's a pretty amazing character. He has I don't know if you've ever read anything about Euler, since we did I bring that book up? Oh, I did. To mention an interesting book. I don't know if they still use in engineering where they ever mentioned Timoshenko. He was a very famous engineer in my generation. So when I was studying, I read some of Timoshenko's theory of elasticity. He has a whole series of books on mechanics. And he also wrote The History of the Strength of Materials. And it's a history of all the great people who contributed, and the how they came up with their calculations and the theory. But it goes from, where does it start? Euler's kind of toward the beginning. I've not read the whole book. Oh my, it starts back with the Greeks, there you go, and the Romans, the aqueducts. So it does give a pretty interesting view, but it's fun to read as you study individual people, just to read a little bit of their history. And of all the people I've ever read about, Euler, I think, is the most incredible person, and had the most interesting life. And in the end, he was just a very, despite a lot of hardships, always a very happy, kind of upbeat person, and ended up dying laughing. In his had a heart attack. He was playing with his granddaughter on his knee after dinner, is the story I read, and he got laughing and couldn't stop laughing and had a heart attack. So I mean, you think, what a way to go! I mean, really great guy. But he was originally Swiss. He grew up near Basel and went to the University of Basel, and his father really. His father was a minister, probably a Calvinist or something, but wanted him to kind of follow in his footsteps. But before he ever went to the university, actually, they had a friend, Bernoulli, which was the father of the famous Bernoulli brothers that did all the calculations on fluid dynamics and fluid flow. And their father was a professor at the university and taught mathematics. It was his specialty. And he kind of he knew the Eulers, and he kind of tutored their son when he must have been like 12 or something, because he went to the university when he was 16. Or let's see, maybe he finished when he was 16. What does it say here? Oh well, whatever. He was pretty young, and the father of Bernoulli was Johann, and he immediately recognized that Euler was a brilliant at math, and he told Euler's father, "Look, no, he could be a minister, but why don't you just let him study math and see how it goes?" And he did. He studied with Bernoulli and was, excelled. He got his degree rather quickly from Basel, and then went on and got I can't read all this. Anyway, the Bernoulli brothers were slightly older than he was, and they went on to St. Petersburg, where they were. This would have been Peter the Great, I think, when he was establishing St. Petersburg, was trying to make it a capital of Europe, and he wanted the finest university in Europe, so he was assembling these great people in different fields from around Europe. So he brought the Bernoulli brothers, and one of them unfortunately got sick and died, and the other one was kind of disheartened and left. But they brought Euler maybe a little bit before that, and Euler ended up taking their place as head of mathematics at the university there. So he was, the head of the whole department of mathematics. He had a great opportunity to do research, and he really excelled at exploring these elastic curves, which is what brought him into the buckling equation. Unfortunately, I think when Peter the Great, I don't know the history real well, I should have gone back and read it, but I think he died, and then there was some wars or something, and there was a little bit of unrest, and he got an offer to go to Berlin from let's see, it would have been Friedrich the Second, their Alpha Fritz was Friedrich the Great, Friedrich the Große, and he brought Euler to his university in Berlin, and he was put in charge of mathematics there, and he did very well, of course. Unfortunately, the other people on the court with Friedrich were not so nice. One was Voltaire, and Voltaire was, from what I've read, was particularly nasty, especially to Euler. For some reason, he didn't agree with Euler, or didn't, and he called, Euler had from early on, he had one eye that was kind of lame, and it lost the sight in that eye, but it hung, and you can see in the photograph a little bit, I guess he's kind of got this eye shut, and Voltaire started calling him the Cyclops, and referred to him as the Cyclops, and really turned Friedrich the Great, against him in a way, and it made it difficult for Euler. There was some project that they assigned him with fountains, that they wanted this fountain garden, and Euler wasn't his thing. It wasn't elasticity. It was just these stupid fountain pressure. Would have been better for Bernoulli to do it, but it didn't turn out real well. And then that, made him, even less appreciated on the court, I think. So eventually, who was it? Catherine, back in Russia, took over. Catherine II, or whoever she was, I forget. And she was having a war with Germany, and came through Berlin, and they actually conquered Berlin, and they were sacking it, and the soldiers looted Euler's home where he was living. And then the captain of the Russian army heard that they had done this and realized it and knew who Euler was. He remembered him from when he was in St. Petersburg. So he came and personally apologized to Euler and set him up, better. And then Catherine heard about it, and she was, shocked that, our beloved Euler, we'd like him back. And so she wrote a letter to him. First she gave him a bunch of money, and then eventually convinced him to come back to St. Petersburg. So he left Friedrich and went to back to St. Petersburg, where he I think either before, I forget when, he married a Russian girl there, and had a family, and lived happily ever after. But he also, his eyesight got worse and worse, and it got to the point that he really couldn't see. But he had assistants, and he said, well, there's no problem. I don't need to see to think. And he would literally dictate these books to these assistants, and he wrote over 400 books. It was the most voluminous author, and is famed for his, he wrote a series of calculus books, which were used as textbooks. I mean, all Europe learned calculus, not from Newton, but from Euler, from his writings on differential equations and everything. He also wrote, which I'd love to read, and I've never had time to do it. When he was with Friedrich in Berlin, almost as a insult, Friedrich told him that he wanted Euler to tutor his, I think it wasn't actually his daughter, I think it was his niece, or, it was a noble young girl who was maybe only, 12 or something, not very old, and he was supposed to tutor her in science and mathematics. So he very graciously said, sure, we can do this. And he wrote a book. It was called Briefe an eine Prinzessin, or something, letters to a young princess. And it became the standard textbook for mathematics and science for all of Europe for like centuries, for till the 1800s sometime. And you can get their copies of it over in the library. I'd love to get it and read it. But it was supposed to be extremely well written as a dialogue, explaining all the science of that time and mathematics, to a young person. And it was just apparently really well written. But later back in St. Petersburg, when he lost his eyesight, he had these assistants, and he just dictated these books. And he'd have like 3 people working on 3 different books, and he'd come over and dictate to this one, and then go to this one and dictate, and 3 books at once. And there was a point when he had an apartment that he used as his office and laboratory, and had all his books in it, and it burned down. And his assistants came to him and they told him, "Oh, Professor Euler, it's terrible. All of your works, all of your books, they're all gone. It was all burnt." And he just kind of said, "Well, it's okay. It's all up here. Get a pencil." And he redictated all these books again. Oh my goodness. So he was quite the character, Yeah. All right. Well, now I've used up too much time. We'll have to pick up there. Okay, and now back to columns. We had been talking about Euler and Euler's wonderful equation here. Oops, let's see. Do I not have my pen turned on? This is the way we usually see Euler's equation. And this is actually the equation we use in wood. And it is exactly the same. It looks a little different, but they've converted the R here to D here, and then the square root of 12, well, it gets squared, so it comes up here. This would be pi squared. Oh, I think it's divided by here. It's in the D, it's divided, and it's divided, and it's in the numerator, so I think it ends up being divided by 12. You can see what that would be. Does that seem about right? Yeah, it would be something like 9 divided by 12. Sounds like about 0.8. But anyway, that's the... so the equations, it is the pure Euler equation, even though it looks a little bit different. But they use D here for the slenderness ratio because it's a lot more convenient with wood, being a rectangular section. You have D as a dimension, so rather than introduce another geometric variable R, and since D is in a rectangle is proportional to R, they just use D. The Euler equation, when you graph it, looks something like this. It's asymptotic to both axes, but there is, of course, a limit in either direction. The limit on the top side would be the crushing or yielding. In wood, it really crushes. And the limit in the other direction is a little bit arbitrary, but it's basically where you're losing so much strength, it's becomes almost unstable. It's a very slender member, and there is a limit to how slender a member you want to allow as a column. In steel, if you're familiar with steel, this limit is 200. So if I can write this out here, in steel, that would be 200. That's based on KL over R. What we have in the usual equation. You can convert the D to R, and if you did, you'd get for wood, I think you have to, what do you have to do? Multiply it by the square root of 12 or something like that, the 50. Normally, this limit for wood is 50. This limit we'll see is limited to 50, but that's LE over D. If we tried to compare it to steel as L over R, then you'd get, I think I worked it out this morning in class, 173. 173, so a little bit less, but essentially in the same range as steel. So although it's a little bit confusing seeing that slenderness limit of 50, you have to remember that's for L over D, not L over R. And it's L over R, you're back in the range, a little bit less in fact than steel, but kind of that same range. Okay, so let's see here. You can think of 3 different ranges. In fact, you could think of it in this, even looking at this graph here, where something in this range would be a short column because it's failing and crushing, and these columns over here are certainly long, they're failing and buckling, and in truth there's an intermediate range where it begins to crush and then it buckles. I mean, for wood. In steel, this would be where you'd start to get flange buckling or web buckling or something like that. The whole section's not buckling, but it's starting to, pieces of it buckle. In wood, I think it's more that it'll start to crush and then it'll buckle. So there is a in between here, an intermediate range. And it used to be, if I remember right, several years ago in wood, they had three separate equations. They had a short equation, an intermediate equation, and a long equation. And now they bring it all together. They've got an equation that gives you essentially this curve, and that's comes from the equation for CP. So they account for buckling the same ways we accounted for stability in beams, with a factor, with a reduction factor, and that CP factor then reduces the stress by the amount here that brings it down to whatever level. Okay, so if there were no buckling, then the wood would crush, and you can see it actually is. I mean, these fibers are kind of buckling, right? You've got fibers that are like little columns themselves, and the fibers are crushing or buckling in the wood, and that produces the crushing. So this would be at the full allowable stress for compression. That's what you'd expect to see, and the the area would be P over the stress, the load over the stress, or the stress is equal to the load over the area. But that would be a short column failure. Long columns, on the other hand, buckle, and this would be the pure Euler buckling equation. This would be, as it reaches, certainly a long column, it would tend to behave in this way. And oh yeah, here it is. This is that 0.82 is simply pi squared over 12, which is coming from the translation of this R to D, right? Okay, but most columns are in between somewhere. They're not so short that they're going to crush, and they're not so long that it's a pure Euler buckling. They're in between, and that's why we use the CP equation to find exactly where on that curve they occur. The thing that of course, what really affects the behavior is the slenderness. The more slender it is, the more likely it is to buckle. And the slenderness in the way we're defining it with the wood is LE over D. And you can see, because wood is rectangular, you have a strong and weak axis, right? You'll have a buckling about the x-axis. If this is the x-axis, then it's buckling about that axis, and it's that would be the strong axis. It has D would be greater, and your slenderness then would be less. As D gets smaller, your slenderness goes up. So when D's 1.5 on a 2x4, that would be buckling about the weak axis. That would be about this axis. It would be buckling this way, and that would be the weak direction. So here you can see this would be the weak direction. That's the way it would normally buckle. Of course, if you brace that weak direction, then maybe it will buckle in the strong axis. It'll buckle in the direction whichever of these slenderness ratios greater. So here, for an unbraced 8-foot piece, we've got in the strong axis of a 2x4 a slenderness of 27, and in the weak axis it's 64, which shows you, wow, okay, that's already greater than the limit of 50. So just as a simple 2x4, like a 2x4 stud in a wall, without any bracing, it would not be allowed at an 8-foot height. You have to put in, and usually we'll add in some sort of bracing to brace the weak axis, or you could skin it with plywood maybe, and count on the plywood as bracing that weak axis. Gypsum board, I don't think, would be a very good thing to rely on for the bracing, particularly if it got wet. It would be lost. So that would probably not be, you shouldn't really count on that for bracing. Along with the height, the end fixity of the column affects the way it buckles, right? If both ends are pinned, which would be the normal condition, then you'll get the full length of it buckling. If one end were fixed and the other end pinned, then you're going to get only that part of it really as representing the curve, and that would be at a ratio of 70% of the original height. That would be 70, and this would be 30 down here, right? And then that becomes the factor, the K factor. Although the recommended value, they assume that this isn't fully fixed, that it maybe twists a little bit and it reduces it. If you've worked with steel, in the steel manual, they get a little bit more precise with this. They look at the stiffness of the beams top and bottom, and they have a wonderful little nomograph where you can plot across and find a more accurate K factor. In wood, in truth, that doesn't happen because the connection between the beams and the columns is really not fixed. It's going to be more of a pinned connection, and so at most you might use this graph. Usually you're going to be using this one right here. This would be the normal condition. If you have one end sunken into a concrete footing, like maybe they do typically with outdoor decks and things, so embed that in concrete. Well, maybe that would give you, I guess you could argue that would give you something like that if the concrete doesn't twist in the dirt. And so you could use perhaps 0.8, but normally you don't get fixity with it. Even if you had a steel bracket around it, the wood can shrink, and then the wood is loose in that steel pocket. Maybe if you have steel plates that are bolted to the wood, and but it could be gets to be a very complicated thing. And then even if it's if it's steel plate that's bolted, then the bolt presses against the wood and has some wiggle room. So it's very difficult to really get that fixity with wood. This is the out of the supplement, right? Happens to be for eastern hemlock balsam fir, and the compression that we're talking about is this one right here, parallel to the grain. This is for columns. This compression perpendicular to the grain is actually bearing. It's not on a column, because this is the direction that's parallel to the grain. That's the way a column's normally oriented. This would be perpendicular to the grain, right? The grain's going this way, so the force, if I put a force on this way, it would be perpendicular to the grain. So if I have a sill plate, we'll look at this a little bit later, a sill plate in a stud wall, and the stud would bear on this sill plate, that would be the bearing stress, C FC perpendicular. But the one we are interested in is this one right here, FC. We also, you'll find you need the E modulus, or E min actually, to calculate the CP factor. So here are the factors that go with our compression. The load duration factor, yes, we're familiar with that. Moisture factor, temperature factor, CF, the size factor, that of course is a little bit different from the bearing, bending factor. Even for dimension lumber, it'll be a different column in that table. As it turns out, for timbers, it's just 1.0. Incising factor, we're familiar with that. And then the new factor, CP, column stability factor. So that's the one that really plays the most significant part and is always present in your column calculation. You're always going to have to calculate CP unless it's totally braced, embedded in a wall or something, in two walls. You're going to have to calculate CP. So this just reviews some of these factors. CD, right? We've talked about that. Those are all the CD factors and the different load combinations. Temperature factor. So here we've got the FC down there. Depending whether it's wet or dry, it's the same factor as for bending for temperature. Here for moisture content, CM. We're over here at this end, and again, you'd need both of these. If moisture is a problem, if it's above 19%, then you're going to need the factor for E min, a factor on E min to calculate the buckling coefficient, the CP, and then this would be the straight CM factor on the compression. And there is a little double asterisk here if it's really low-grade wood. If it's less than 750 psi in compression, then you don't need to worry about the moisture. The moisture's, you don't need to reduce it any further. Apparently 1.0 can be taken. And then these are all the factors for CF, the CF factors. CF. Okay. And this is for the timbers. It's a little bit different for the timbers, particularly CF, as I mentioned, for timbers, is 1.0 for compression. So you don't need to worry about CF really for the timbers. And the moisture content is also a little bit different, right? It's those numbers, 1.0 for the E modulus. And this is the incising factor. Here's where it comes in. So it would, if you have incising, and this would, yeah, that is not uncommon for some columns, big timber columns that would have incising on them. You see it a lot on telephone poles for some reason. I guess they're all chemically treated. Okay, and now the CP factor, the big one. And you can see it's a formula very similar to the CL formula that we used. A little bit of difference. They introduce another variable C down here rather than just using the same value across it all. It varies slightly between sawn lumber, which would be either dimension lumber or timbers, anything sawn, versus round timbers or poles, telephone poles maybe, that kind of thing, a little bit higher, or glue laminated timber is the highest. So there's a little bit of variation in that factor. Otherwise, we calculate the Euler buckling, and we look at a ratio between the Euler buckling and the factored compressive stress. This has got all the factors on it except CP. Of course, you're trying to calculate CP. So you have to calculate, or at least find, all the other factors first, and then CP is always the last one you do, since you've got to have the others to do that FC asterisk. There is, again, over here, they mentioned the limit of 50 for the slenderness ratio. And you do have to pay attention to the different L over D's, right? Whoops. And if you graph that out, you get something that looks pretty similar to this. This is one I did some years ago, and I can't really remember what size wood it was based on. You realize it will, and you can't use this for everything. This is an approximation, but it does look, when you graph it, something like this, which is what the buckling behavior looks like, really. It's just, if you were graphing the Euler equation, well, of course, the pure Euler equation's not going to have the curve at the end. The Euler equation was what we saw before, where it goes asymptotic to both axes. But this is modified so that it's tapering off here. That would be the limit of crushing, and as it gets longer, it gets less and less stable, and it loses strength down at this end. This curve will vary, of course, on your grade of lumber influences it. The slenderness ratio influences it. The E modulus, of course, influences. So there are. That's what I'm just saying. This is not an absolute curve that's correct for any column. It was one specific column, but they are pretty similar, and you can kind of have this picture in your mind that it ranges. At 50, it's down about, 0.15, right? Is what 50 looks like, or not even. It's even lower. Maybe I should have said 1.2. And up here, if you had a very low slenderness, you're getting closer to 1. And if you're in the middle, at say you're right in the middle, half of 50 is 25. Well, then you're almost at 0.5. This would be 0.5. It looks a little bit above 0.5, maybe 0.53 or something, right? So that gives you a kind of a range that if you have a slenderness that's smaller than 25, then you should be in the upper half, right? It should be 0.6, 7, 8, somewhere up in there. If you have a slenderness that's longer than 25, you're moving toward 50, then it's going to go down, and you'll have a CP that's much lower. And of course, the lower the CP goes, that's reducing the strength, reducing the stress value. So we could do a lovely little example here. This is an analysis example, and a simple pass-fail analysis. So we're given the size, given the length, all the support conditions, we're given the load here, we're given the material properties. The only thing we don't know, well, what we're trying to see is whether it's safe or not, pass or fail. So when we're given all the dimensions, we can immediately calculate the slenderness ratio, make sure that it's below 50. Then we can calculate all the other adjustment factors, and we get CP last once we've got all the other ones. And then once we've got that, we can calculate F prime C, and that is the allowable stress. That's how much is allowed. And the actual stress is simply P over A. And we've already got both P and A. So we just find the actual stress and compare the two. And if the actual stress is less than what's allowed, then everything's okay. If it gets to be greater than what's allowed, then you've got problems. Then it fails. Okay. So here's a lovely example. This is, in fact, I was telling the class today, this looks like, reminds me of the pole barn that my son was working on. It's maybe a little bit taller than that, but this is not a stud wall. This is like the wall in a larger shed type building, maybe with the roof coming down on it. Yeah, apparently a roof coming on it because it's that load is coming from a snow load, and it is braced partially. It has some sort of bracing on it, and it's the strong axis height. It's a 4x8, so it looks like, you know, like that, right? There's a that's 4x8, right? So the strong axis buckling out of the wall would be in the 8-inch direction, and that's with the full 25-foot height. And the weak axis is going to be going, you know, like this, and the because of the way the bracing's set up, it's not totally even. The longer one is going to be that 10 foot in the middle, a little bit longer. So we've got to check our slenderness ratios. We've got to check, we start maybe by looking up in the NDS for, well, we've got Doug Fir Larch number 1. Ooh, a really strong wood, 1500 PSI. Good bit stronger. Oh, we looked up in class today, just to compare it. Our wood of the day was yellow poplar, and we said that was kind of moderately strength. Oops, come on, where is it? It is in the NDS though. Yellow poplar is. Compression value 9. Select structural. This is number 1. Number 1 is 725. So 725. Oh, not even half of what Doug Fir gives us. So Doug Fir's a lot. Sorry, yellow poplar. Doug Fir's a lot stronger than the yellow poplar, I guess. And let's see. Let's gather up some of these factors then. The adjustment factors. For snow load, our CD is 1.5. There's no moisture. There's no temperature is not elevated. CF we can look up. In fact, that's this chart right here for compression. And we've got a 4x8. So an 8-inch member. It looks like 1.05. So there we go. 1.05. And it doesn't have any incising, so that's not a problem. CP. We've got to calculate CP. So we got enough of everything else. Now we can go ahead and calculate CP. Here's the lovely equation. And we start by finding which slenderness ratio governs. So in the 25-foot direction, that's 300 inches over 7.25, which is the dimension lumber 4x8. Versus 10 feet, 120 inches on the 3.5-inch direction. So that gives us 34, but this gives us 41. So 41 is the one that's going to control. It's less than 50, so that's passing, but it's getting up there pretty close to 50. So you could think of that graph, and you'd say, well, okay, 1 point something. I don't know if it'd even make it to 2 point, because that graph tapers off at the bottom. It was all down there at 1 point something. Everything between 50 and 40, I think. So you could make a guess, like one. I mean, just to before you work such a enormous equation, it's good to have some sort of an idea what you're expecting for the result. And I would think 1 point something, 1.5, 1 point something. Okay, so let's go ahead and do the calculations then. The Euler buckling, this is with the slenderness we just calculated. That comes out not terribly high, 297. The FC for our lovely Doug Fir, it is even raised a little with the snow coefficient. So that's way up at 1800. Wow, so a large discrepancy. This factor then is 0.164, pretty small, and the C that goes in down here is for the sawn lumber, 0.8. So we run all that through, and what do we come up with? Hey, that's about right. 1.584. There it is. 1.584. Okay, so now we can get our allowable stress. We put all the factors in there, the CD, and this was CF, I think, and CP on the end, and it drops it down to 286 from 1800. Wow, drops it down to 286 or 287 almost, and so that's the allowable stress. Then we can calculate the actual stress. We had a load coming on it of 7,000. That's the point load, and the area of that 4x8 is 25, a little over 25. So the stress comes out to be 275. So it's enough area, and it looks like the 286 is greater than 275, right? So it works out. That one's safe. Passes. Okay, so now we can look at, this is a capacity example. So again, it is a type of analysis. We're given the size and the length and all the support conditions and the material, but what we don't know is what the load is. So we're going to look, this is what we're looking for. We're looking for the load up there. So it starts out exactly the same. We do the slenderness calculation, check that, get all our factors, find CP, find the allowable stress. Then once we have the allowable stress, instead of comparing it to the actual stress, we can't really calculate the actual stress because we don't have the load. We set the actual stress equal to the allowable stress. So we're raising the actual stress to the highest level that's allowed, the full allowable stress. And then we calculate the load based on that. So here's another example, a little bit different, slightly larger. Remember, we got a 4x10 now. And Hemfer, number 2, a little bit lower grade. But this one, and this one's subjected to some moisture. Got a little bit of moisture on this, so 20%, we're going to have to calculate our moisture factor. It's only 8 feet tall, right? And it's braced at half height. So these are 4 foot and 4 foot. Okay, so that's 96 inches. To get the slenderness ratio will be 10 on the 8 foot direction, 13 on the braced weak axis. So it's a little bit worse on the weak axis, even with the bracing, 13.7. But it's, you know, if you're thinking of that curve, right? If I can draw that out, if this is my 50 and this is 25, 13 is about half of 25, isn't it? It's about in there. So it should be pretty high. Should be a little bit on the higher side, maybe I don't know, 0.7, 0.8, maybe, something about there. That would be a guess as to what the CP is going to come out. So we could guess maybe let's say 0.75, between 7 and 8. Something like that would be a guess. Okay, the others we can calculate. This is coming from a wind load, we said. Okay, so there's for wind. It does have moisture on it, so we're going to look up the moisture factor. No temperature, no
oh, yeah, we do have to look at that up. It looks like it came out to be 1.0, but let's see what some of these factors are. So here's the moisture factor. There's the 0.8 and the 0.9. We'll need both of those. And it is over 750 wood. We have 1300, I think. Yeah. And, well, times CF. What is CF? We've got a 10, a 2 by 10. So that looks like we've got 1.0. So there's the 1.0 for CF. So that does check then. That's not an issue. So we're going to use those two. So those are the factors that we need. Now we can go ahead and calculate CP. Get the slenderness. This is the slenderness that we're using, and we get the Euler stress. Quite a bit higher. Wow. Remember the other one with the much larger slenderness ratio was very low. It was only a couple hundred or something, wasn't it? Now this one's up at 1800, higher than the actual tabulated stress. So we put the factors on that, and we get the ratio. It's now above 1.1. That goes in there and there and there. And we are using, this is still dimension lumber, so my C is 0.8. And we do that calculation, and it comes out to be, here it is, 0.72. Okay, so almost 0.73. Well, we were in the ballpark. I guess we were guessing 0.75. That looks like we were pretty close. Okay, so now we have to put that value in along with the CD, and this was CM, and that's now CP. So that gives us a compressive stress of 1208, and now we take that as the maximum allowable, multiply it by the area, and that'll give us the maximum allowable capacity load. So almost 40 kips, 39.1 kips would be the capacity. Okay, so that's got that guy. Now the very last one we'll do here is a timber column. Okay, and we'll do this as a design problem. And this procedure, design procedure, is the same whether it's timbers or dimension lumber. Doesn't really make any difference. It's just I did this one with timbers to be because we haven't done one with timber yet. So this one's with a timber size. But the like a lot of design problems, you don't have enough data at the beginning of it to totally determine the size. Meaning the conditions of use, particularly CP and CF, depend on the size, right? And what are we trying to find? The size. So we can't get the values to determine the size until we have the size. So this is the dilemma that you're always in with design, or a lot of times with the design problems, and it leads to an iteration. You have to estimate something, estimate the area, estimate the size of the column, calculate it all the way through, revise it, recalculate this, and then start over. Come back up here, and maybe it was where we guessed CP. Now you've got a CP. So there is an iteration here that you go through. You make a guess. You could do it, and you can make guesses at different things, I guess. You could just guess the size of the column and then analyze it and see whether you've got to go bigger or smaller. In this case, I guess I made a guess at CP, but whatever you guess, you could guess the size is probably easier to guess. Particularly if you have tables. You'll see there's some tables that make it a little bit easier to guess the size. Okay, so here's an example. White oak number 1. Okay, got some hardwood here. It's going to be used dry, right? So this is going to be 1.0. Normal temperature, so that'll be 1.0. It's not incised, so incising is 1. So we don't know CF, and we don't, let's see, we should know that. This is live load, so that's also 1. So everything's 1 there. We could maybe guess C. Oh, we do know CF. Timber, all the timbers for CF are 1.0, I believe. So that's also 1.0. So the only one we don't know is CP. And in this one, I made a guess at CP. Like I said, you could guess the area maybe as a starting point, but I just took a middle value, right in the middle, 0.5, and said I'd try that. So the we're going to have to get the stress. This is white oak number 1, and it is a post and timber here. Make sure you get the right column, number 1, and this looks like the number we want, 825, and we also want E min, I believe, for buckling, for the Euler equation, 370. So those are those 2 numbers I want there. Then I've got to calculate the load that's coming on here. I've got 55, looks like 55 PSF, and it's on 256. So I'm going to say 55 times 256, and that's going to give me P. I don't see my calculator. Somehow I don't have my calculator here, but that will be our load. Here it is. This must be it. 14,080 pounds. Okay, a little hard to read. Sorry. 14,080. That's that number down there. Okay, so I'm guessing I'm going to calculate the area here so that I can choose a member, and I'll take that load. The load divided by the stress is going to give me the area, and I'm guessing the CP value, and this was what I had out of the table. So I come out with a required area of 34 square inches. So taking the square root of 34, just assuming it's going to be a square column, looks like about 5.8 inches. So as a guess, that was close maybe to 5.5. It's kind of going down a little bit. You know, maybe I was low on my 0.5 guess. I don't know. So 5.5. So I could say a 6 by 6. This is what I'm guessing. A 6 by 6 column. So we will try a 6 by 6. So now I've got the size. I can actually just go through the analysis procedure, right? I've got the size. I can calculate a slenderness ratio based on the 12-foot height. I can then kind of guess, 26. Yeah, well, 0.5 wasn't a bad guess then. Maybe if it's coming out at 26. We calculate an Euler stress. We get the FC asterisk. Those were all 1, right? 1.0. That's supposed to be 1. And that gives us the stress doesn't change much there. But then when I calculate CP, this is about in the middle too, and it comes out a little bit below 0.5 actually, but okay, pretty close to 0.5. It's probably correct. But that means my guess at 0.5 was optimistic. So it's going to be require more area. Since the CP is lower, the stress is going to be lower. I'll have to have more area to carry the load. And I already I rounded up, didn't I? I mean, I went down. It was telling me I needed 5.8, and I went to 5.5. I went just the wrong direction. I should have gone to 6.6 or something, because now that's going to fail for sure. And you can, well, okay, yeah, here's the 26 is giving me about, I don't know, it's in there. Okay, so I've got to revise my FC. Now I've got a more accurate CP. I put that in my F prime C and get a revised A, and I see, oh yeah, the A for the 6x6 is only 30. I need 37, so the 6x6 failed. So looking at looking at some properties here, what do I need? I need 37, so that one failed. Any of these would pass, right? So I don't have to really go up to an 8x8. I could do a 6x8 maybe. At any rate, that's one I chose. That's one I'm going to try, is the 6x8. And that'll have 41.25. It should work. So we calculate the slenderness ratio on that. It still has the same, buckling's going to be about the same axis, right? It's still the 6-inch weak axis. So the slenderness ratio actually doesn't change. The CP then doesn't change since the slenderness ratio didn't change. And if the CP didn't change, then my CF doesn't change, and that means this is still correct. Nothing changed. So that one should indeed pass. Right, that one passes, the 6x8. So that's all there is to that. Now I could show you one other thing. There are tables that make this an awful lot easier. I'm looking around to where I had these. There's some manuals. This table is actually out of the 2005 edition. These come with the NDS. It's published also by the American Wood Council. But I don't think, I meant to look online, I don't think there is one for the 2018 version. They don't publish them every year. This one is 2012, and oddly enough, the 2012 is thinner than the 2005. And I was looking through it this morning. What they cut out was this table. They cut out the columns. I don't know, maybe they decided there weren't enough examples in there, or I don't know what it was, but they cut out the column table. But you can look at that manual. They do give quite a few different tables in it, also for span tables, flexure tables. And this column table is kind of useful, at least for, it worked for this example. Hem fir, you can see actually we were using grade number 2, right, if I'm correct, and a 6x8 in grade number 2. This is the weak axis buckling, would be 14,800. So we were required to have, what would I have to have? I think it was 14,300 or something. 1408, 14. So I'm required to have 14,080 and pounds, and here 14,800 is greater. So this would work. So this proves, I guess, that very simply, right? It takes like 10 seconds to pick it out of the table. 1408 would work. You can also see on here it works for 12 feet, right? That's a 12-foot height that we were using. They give you all the way down to 2 feet. Wow, what a 2-foot column's pretty short, huh? And up to 16 feet. This also, if I had wanted to go to select structural, it looks like the 6x6 would have worked at select structural. Here I get 14,300, which would be stronger than the needed 14,000 is all I needed. Instead, this has got 14,300. So anyway, these tables are available. You can, if you can find them. I think this is, I'll look and make sure, but I believe it's posted on the Canvas site. This should be up there. All right, so that gives you kind of an overview with the columns. You can see from stud wall design or analysis, or even this example with column design, you got a pretty good range of things you can do with the columns.